Good afternoon. My name is Yi Hai. I'm from Monash University in Melbourne, Australia. And I did my PhD with Dr. Cho in Georgia Tech. And he asked me to present their work on behalf of them. So please forgive me if I sound like not knowing what I'm talking about. And I'm happy to direct your questions to Dr. Cho. So the topic is automated collaboration framework of UAV and UGV for 3D visualization of construction sites. So the UGV here stands for unmanned ground vehicle. And I'll explain what that means later. So we have been talking about smart construction lately. And then, in my opinion, what makes construction smart is the underlying data and the information we can derive from this data. And among different types of data, the up-to-date and accurate geometric data is of great value in terms of understanding the construction progress or understand the safety conditions of the construction site. And in the past, it's actually very labor-intensive and time-consuming to collect up-to-date geometric data of the site. But now we have the tools such as unmanned aerial vehicle, drones, to help us taking pictures and using photogrammetry to generate point cloud or mesh of the construction site. But there are some limitations just using UAV and photogrammetry. So for example, the UAV flying above the structure or above the site will generate a point cloud with good coverage and accuracy for horizontal planes. But for vertical structures or vertical components, there are occlusion problems. And this is actually related to Jack's question in John's keynote. Like in Hong Kong, with those high skyscrapers, the ground level will be missed from aerial photography. And using terrestrial laser scanners or ground-based robots to scan the site, we usually miss the occluded part of the structure or the roof component. So if somehow we can combine these two point cloud sources, then we can get a more complete point cloud or more complete geometric data of the construction site. So this is the basic idea and motivation of this study. So the overarching aim of this study is to create a automated framework for the collaboration of UAV and UGV for 3D visualization. And the first task in this study is to use the UAV-generated data, the point cloud, to help plan the UGV, the unmanned ground vehicle scanning task. And the second part is, once we have the point cloud from UAV and UGV, how do we integrate this data together in order to get a more comprehensive and accurate point cloud data? So the left side is showing a overall workflow of this framework. So firstly, the UAV is deployed to take pictures of the site, and then using photogrammetry to generate a point cloud. And most likely, this point cloud will have occlusions and blind spots. So this is where the first part of this framework, the methodology, which is path or mission planning for the unmanned ground vehicle. So on the right side is a more detailed workflow of the path planning task. So firstly, we have the photogrammetry point cloud from UAV, and using that we can create a gradient map for the construction site, based on which we can identify the movable areas or the flat areas for the unmanned ground vehicle or the robot to navigate through the site. And then based on line of sight simulation, using ray tracing, we can find the optimal scan locations for the UGV to stop and scan the site, so that we can maximize the point we get from the laser scan and to avoid occlusions. And once the UGV operation is completed and we have the point cloud, now the task is to match the point cloud from the UGV and UAV together. So here, there are many people doing point cloud registration, and most of them are based on the points. So try to match the point features from different point cloud datasets. But here the challenge is the UAV generated point cloud is of a different scale of the laser scanner point cloud, which create a big challenge in using such methods. So here what the team proposed is to use the image as the data to do the point cloud matching or registration. So the image taken by the UAV is has a metadata of where the picture is taken and the orientation of the lens. And then in the UGV, it has the laser scan. I'll show you how the UGV looks like, but it has laser scanners and also a camera. So the camera there, the main purpose is to capture the RGB color information to match it to the point cloud, just as the commercial laser scanners. But we can use that image with the image captured by the UAV to find the matching points and find the transformation matrix between these two data frames. And then we can, based on this mapping, we can register these two point cloud data sets. And then that's the rough registration, and eventually you can use ICP, iterative closest point, to do a fine registration. So let me show you how the approach was tested and validated in a field test. So this is a site in Georgia Tech's structures lab. And this picture shows you the test site. It has a 2-story concrete structure, and the entire site is pretty congested with many waste and structure components laying on the site. And we use a UAV, a commercial UAV, and use the Pix 4D, one of the commercial flight planners, to plan the UAV photogrammetry task. And then for the UGV, this machine is designed in-house. So we designed that with 5 2D LiDARs with a DSLR camera. And this UGV itself can have its own mission planner, so it can navigate through the site and using SLAM to avoid collisions. So following the methodology I introduced earlier, so firstly, the UAV flies around the site and take pictures, generates point cloud from photogrammetry. So that's the initial map. And based on that, we can construct a gradient map to show the accessible areas for the UGV. And then based on line of sight simulation, we can find the optimal scan locations in this site. So in this particular case study, there were 5 scan locations identified. So basically, the UGV will navigate through the site and stop at these 5 locations and do the scan and move again to the next scan location. So this whole process is autonomous. So no worker or human beings has to be involved. And this slide shows you the result. So the left side is the image matching. So there are the common features identified from the 2 image frames. And then this transformation is used to register the 2 point cloud data sets. And in the initial alignment, you can see the different color. The true color shows the true color data set shows the point cloud from UAV, and the blue ones is from the UGV. And then in the fine registration, eventually the registration error is 0.1 meters. So this slide shows a different part of the site, how this collaborative process will produce a more complete point cloud at the end. So the first row is the point cloud captured by the UAV and then by the UGV. And at the bottom is the, sorry, oops, just jumps back. At the bottom is the integrated point cloud at the end. And I have a video showing how the approach works in this field test. There are 4 LiDARs mounted on the rotating platform, and then there's another LiDAR in front of the rotating part, which is used for SLAM navigation. And now it stops to do the laser scan, and you can see each of the scanners are scanning 1/4 of the space. And now we have a complete point cloud from the UGV. Let me just jump to the results. So these are the point cloud data sets collected from the UAV and UGV respectively. And this is the end result from this process. So in this study, we propose a framework for fully automated UAV and UGV collaboration, and the aim is to generate a more complete point cloud of the site, trying to assist decision making. And again, the first task was to, based on the UAV data, to do the path planning for the UGV, and then to register the point cloud data from UAV and UGV. And the field test shows that this process can successfully fill several occlusions exist in the respective point cloud. And that's all about this presentation, and I'm happy to take questions or pass your questions to Dr. Cho. And here's his email if you are interested in reaching out. Thank you.